this chapter, I think we'll continue on about the crystallinity. We have talked about how to, what is the importance of the crystallinity and how to calculate the crystallinity by measuring the density. Okay? If you remember the equations that I have elaborated very quickly, if you know the density of the specimen and the density of the crystalline portion and the amorphous portion, you will be able to calculate the crystallinity. Okay, so most of the polymers are, generally the semi-crystalline, meaning that some portion of your polymer is crystalline, whereas the rest of them are amorphous portion. Okay? So this is the equation that I have elaborated a little bit, and we have already talked about the packing. The packing density is very important. So the packing means that if your molecule is linearly aligned, then your packing density is pretty high, so that you will be able to make the crystalline materials, and the degree of crystallinity, of course, will be very high. Okay? Also, the secondary bonding forces, such as the hydrogen bonding, is very important. So between the molecules, the intermolecular hydrogen bonding is important to make your crystalline portions. Okay? And we have already talked about the effect of stretching, the orientation. Okay? So if your material is aligned in such a way that the molecules can be packed very effectively, then you will increase the crystallinity as well. And I think we have already talked about this. And also the cooling rate, okay? Rate of cooling. If you have a rapid cooling and a slow cooling, then if you have rapid cooling and a slow cooling, then the material will be less crystalline or the more crystalline, depending upon the cooling rates, as well as linearity, and the cross-linked structure will influence the crystallinity as well. We have talked about the importance of the glass transition temperature and the melting temperature, and I have emphasized that the melting temperature may not be present in polymers, but glass transition temperature should be present in the polymeric system. Okay? The TG is an essential part of the polymer, whereas melting temperature may not, depending upon your crystallinity. Okay? If you have 100% amorphous structure, such as the rubbery polymer, then you don't have any melting points, and your melting temperature will not present. Okay? Whereas the glass transition temperature should be in the polymeric systems. And I think the rate of crystallization influences these crystallization as well. So crystallization always occurs between glass transition temperature and the melting temperature. Okay, the melting temperature, above the melting temperature, your crystals melts. So it's in the liquid phase, okay, above the melting temperature, so you don't find any the melting behaviors. Okay, crystals cannot be detected above the melting temperature, but below the melting temperature, you can detect the melting. And rate of polymerization, rate of crystallization. In other words, if you cool down your melts and lowering to the room temperature or whatever, then you can detect the crystallization peaks. So crystallization peaks always appear if you cool down. If you increase the temperature, perhaps not. Okay. And so the rate of crystallization always occurs between this glass transition temperature and melting temperature. And next slide, I think I will show you how we can measure the crystallization peaks, okay, and the melting peaks. Okay. Oops. Okay, we talked about the larger crystals and smaller crystals. Smaller crystals appear if you have a rapid cooling. Okay. If you cool down your melts very quickly, then you have a nuclei, and you have a growth of your the crystals, but there is not enough time for your crystals to grow, so the crystals remain very small. Okay? Although you have a large number of crystals, you have many crystals, but the growth is not enough because you don't have any much time. Okay? So time and temperature is quite closely related. Okay? So we call it as a Boltzmann principle, time-temperature superposition principle. But anyway, the time and temperature is quite related with the rate of your the cooling. Okay? So this is the case for rapid cooling, and if you cool down very slowly, meaning that it took a long time, so that your small crystals can become coalescence, aggregates, gather together, so your crystals will grow, okay, because you have enough time to grow. Okay? So the crystals become larger. It looks like something like this. Okay? So depending upon the cooling rate, you have a different shape and different number of crystals within a given space. I'm not saying that which is better, but the crystals are in different shape, or in different length or the width, the magnitude. So most of the polymers are semi-crystalline. I'm not saying that this is the 50% crystalline portion, but maybe 30%, maybe 70%, maybe 50%. Okay, semi means very. There is not a definite term, but it's indefinite term. So you don't know which, how many of the semi means. Okay? But we can detect, we can explain the several shapes of the crystals, right, in different forms. Okay? First model, and I will show you several models of the crystals. Right? Models of the crystals. First of all, I will show you the fringed micelle model. Fringed micelle model means that the crystals are spread in the amorphous matrices. Okay? Well, we have some shape of crystals, and I have emphasized that your crystals are embedded in the amorphous portion, and it looks like something like this. Okay? The left-hand side is the one that this one line is something like a polymer, linear polymers. Okay? We have many linear polymers. Okay? One linear polymer will, if you follow, will go over here. Okay? Well, you may have a large number of them, but I think we can just pick up, this length, and you have many types of linear polymers. Some polymers are in the linearity, okay, and some of them are not. Okay, if you think about the larger, the many, strings, okay, strings. Well, those strings might be, packed something like this in linear form, or some of them are in random forms. Okay? Okay? If you increase the temperature and stretch in such a way that those linear polymers are aligned together, okay, then you can have a different shape of the crystal forms and the amorphous forms. This is the effect of orientation in the picture in the right-hand side. Okay? Left-hand side is just right after without any orientation, but this is the case for the orientation or stretching. Okay? Stretching, therefore, will increase the linearity, okay? Because you can find many of them are linear portions. So, therefore, the crystallinity increases as you increase the orientation and stretching. Okay? Now, these linear forms are crystalline forms, and the kinked forms or the randomly aligned form is amorphous portion. So you see, the crystallites are embedded in amorphous matrices. If you stretch, those crystals remain in the crystalline portion, whereas amorphous portion may be aligned so that crystallinity increases, as you can see here. Okay? So this is what they call the fringed micelle model. And you can find in your textbook and others, you will see a lot of these types of pictures, and this is the same. Okay, so if you look at this picture, this is the unoriented form of the semi-crystalline polymers, whereas this is the oriented form of the semi-crystalline polymers. Okay? The second model is a folded chain crystal model. Folded chain crystal model. Back in 1966, Dr. Peter Lin at the National Institute of Science and Technology, NIST, in Washington, D.C., and what he has done was that he melts the polyethylene at high temperature. You see, the polyethylene, the CH2 and CH2 is connected to each other. It's a linear polymer. So, you know the angle between the carbon and carbon, okay? Carbon and carbon, and the 109 degree because it's sp3 hybridized structure, okay? And you know the length between the carbon and carbon is about what? 1.54 Armstrong, right? And because assuming that you have a linear form, okay, and you know the molecular weight, therefore you know the distance between the end to end, okay, of one chain. Okay? So he assumed that, well, because the molecular weight may be high, maybe several hundred thousand, so he can calculate the length, okay? Assuming that this is linearly stretched. Okay? But what he found was that he took a picture. This is the transmission electron microscopy picture of the crystals of the polyethylene at melt state, okay, at molten state. And what he found was that you see, these are the crystals, and the crystals are overlapped one another. Okay? In other words, if you look at this picture from here to here, well, there are two crystals, but this overlapped layer can be detected because of the colors. Okay, colors are a little darker here, so that two crystals are overlapped each other, and you see the edges, the white lines. These white lines can be detected because if you tilt a little bit, then there is a shadow, and this white line means that there is the shadow, which means that you have a length of the crystals. Okay, and these are the width of the crystals. Okay? Because you know the magnitude, okay, the length, the scale of this transmission electron microscope, he can detect this shadow length. In other words, length of the crystals. This length of the crystals are not the same as the length of the total, the whole chain. And what he can imagine was that the length or the thickness of this crystal is only about 10 nanometer, which is about 100 Armstrong, right? 100 Armstrong, whereas his chain, polyethylene chain, is much, much larger, assuming that this is about more than 1,000 Armstrong of the total length, and he can only find the length, the width, thickness is only about 100 Armstrong. So what happened was that maybe the crystal linear polymer will grow, okay, it will be linearly growing from bottom to top, but at a certain critical length, it will be folded down, then up and down, and so on. So the crystals are aligned in such a way that you can see these lines. If you stretch them, well, this will be the total length, but the crystal grow, perpendicular to the plane. Okay? This is what he assumes, and he can. This is the only explanation that he can, discuss to the other people with this transmission electron microscope, and this is what they call is a folded chain crystallites. Okay, and this is understandable because if your chain will grow, okay, such as hair. If you think about your hair, at a certain length, your hair will align in perpendicular to your body, growing to the sky, but at a certain critical length, it will be folding, okay? Right? So most of your hair, because your hair is too long, I think you're aligned to the same body positions. But I think if your hair is too short, yes, it will not be folding, but it's just growing perpendicular to your body. Okay, and this is what understandable and reasonable explanation, and this is what they call is a folded chain crystallites. Okay, so folded chain crystallites can be formed using the dilute polymer solution. Dilute polymer solution. Dilute means dilution. Okay, it's not concentrated. It's the opposite to the concentrate. Okay? Dilute means that your polymer is diluted in a large amount of solvents. Okay? Then you will, and if you cool down, the solvent is evaporated very quickly, then you can form the folded chain crystals. Okay. So there are some of the models. Okay. The third model that we can explain about the crystals is extended chain crystal model. Extended chain crystal model can only be found in the molten state. If you don't have any solvent, but if you increase the temperature of your polyethylene crystals, okay, then you form, and then you orientate them or stretch them. The crystals will grow in such a way that it looks like a shish kebab. Okay? Shish kebab, you know the shish kebab. Kuch. This is what they call the shish kebab. Okay, so this is a linear portion of the polymer where your crystals grow in such a way there is like a folded crystals. So folded crystals and the extension of the crystals gather together to form the extended chain crystals. Okay. This model can be found only at the molten state of your polymer. Molten means that you melt your polymer without any solvents. Fourth model is the spherulite model. Spherulite model is the one that you found at the slow cooling rate, the picture. Spherulite is the one that you have a lamella structure. I think I forgot to mention about the lamella structure. Lamella structure is the chain folded model. Okay, that is what they call the lamella. Okay? You have a lamella, and you have an amorphous portion between the lamella or crystals, but you have a nuclei, just like a crystal, just like ice crystals on the glass when you have a very cold in the winter. Okay? Cold in the winter, the water will attach to the lower glass side of your room. Okay. And because the temperature is very cold in the outside, so that your water will become ice, and you see the ice will grow just like a spherulite. This is what they call the spherulite structure. So if you look at this picture, this is the polarizing light microscopy picture, and you see this is the nuclei. Nuclei will grow so that you form a very different color, and it extends to in such a way that another layer will grow. So you have a boundary between the crystal and crystals. and it stops because of the interruption between the two crystals. And you see the interlayer structure between the two crystals, but this is what they call the spherolytic structure. You see a lot of these lamellas and amorphous portion, but these are the crystalline spherolytic structures. And this is also the representative picture in many of the textbooks as well in polymer science. Okay. Okay. So these are the four representative crystalline models. Okay. You can find many other crystalline models as well if you synthesize new polymers. Okay. But if you found the unfound the crystalline structure, you can publish the paper, okay, and because it's a new finding. Okay? New finding can be reported in the journal. This is what we call the article, okay, research article. And if you found a new crystalline form of your new polymers, then it will be reported in the journal as an article. So these are the four representative crystalline structures that I can present to you. And next topic that I will, that we can discuss is how we can detect the crystalline structures. Right? How we can detect the crystalline structures. Well, crystalline structures can be because this chapter we talked about the semi-crystalline polymers. Semi-crystalline polymer means that we have some portion of crystals, and the rest of them are amorphous portion. If we can find the way of measuring the glass transition temperature and the melting temperature, okay, and the melting temperature, they'll be nice. And the TM, melting temperature, can be found can be measured by one of the instrument called the differential scanning calorimetry, DSC. And if you remember about the X-ray diffraction patterns in your general chemistry or physical chemistry, you can find the crystallinity as well. So I would like to introduce you two techniques to measure the crystallinity. Right? So first of all, the differential scanning the DSC, differential scanning calorimetry technique. Okay? Differential scanning calorimetry technique is the one that you should have one of the block made of metals. Inside of this adiabatic chamber, if you open this adiabatic chamber, we have two platforms. Okay? These two platforms look something like this. Okay? On top of these two platforms, the metal platforms, we add the one of this is the reference platform. The second one is a sample platform. Okay? These are made of metals. Now, this reference platform is as name says, it's a reference. And in this the platform, this is the sample platform. So you put the sample on top of this platform, whereas this is used as a reference platform. So what we are doing is that on top of this platform, we add the very small, tiny the pans, and I have the very tiny pans. These are the aluminum pans, very small, the very tiny the aluminum pans with the very small size, and this pan is consisted of the bottom portion and top portion. Okay, so this bottom portion of this pan, sample pan, a very small one. I think I will circulate them. On top of this very small, tiny sample pan, you put a small amount of polymer samples, such as 10 milligrams or 20 milligrams of your sample by measuring in your from the balance. Okay? So on top of this very small, tiny sample pan, you add the samples, and you add the lid, okay, top portion, on top of the sample pan, and clamp it, okay, and then clamp it, and this clamped one looks something like this. So I will circulate them. Okay. Anyway, we need the two pans. Okay. One pan, the first pan is empty. You just have an empty one without any sample. Okay, without any sample, you just put these empty pans, but pressed one on top of this reference platform. And the second one is the one that contains the samples. Okay, okay. So you put the two pans without any sample. This contains small amount of your samples. Okay. So I'll circulate them. 하나가 뚜껑이 조금 닫히긴 했는데요. 찍진 않았어요. 열어보세요. So okay. Anyway, you have two pans. One contains samples. The second one without any samples. Okay. That's why we call this as a reference pan, reference platform. This is the sample platform. Now below this metal part, we have a thermocouple, two thermocouples. Thermocouple detects the temperature of your sample, of your pans. Okay? So underneath, right beneath this platform, we have a thermocouple which can detect. It's like a thermometer. Okay? This is what they call the chromel detector, chromel area detector, something like that. Chromel wire is embedded right underneath this the pans, two pans. So if there is any phase changes, if there is any phase changes because of the exothermic reaction or endothermic reaction, exothermic reaction means what? Your heat is flowing out from your system. Endothermic means you absorb your heat from the surroundings to your systems, right? So if there is any changes of your heat flow because of endothermic and exothermic behaviors of your polymer, then the temperature changes, right? If the sample, okay, if a sample has an exothermic behaviors, meaning that your heat is flowing from your polymeric system out to the surroundings, then temperature just right beneath this sample pan may decrease because of the heat flow out through the surroundings, right? If there is any heat absorbing from the surrounding to the system, then your temperature will increase, right? So temperature can be detected because of the endothermic and endothermic reaction of your polymer from your the specimen platforms. Now, reference means that without any sample, your rate of increase of your temperature is just a constant, right? If you hit your and if you order your machine with a heating rate, constant heating rate, for example, 10 degrees C per minute, then your surrounding, all this adiabatic chamber will increase its temperature at 10 degrees C per minute, right? But if there is, but for this sample platform, it's not. Okay? It will increase, of course, but if there is any endothermic or exothermic reaction, the heat flow may not be the same as the constant. Okay? So because the polymer we have two different types of the heat flows. exothermic and endothermic, the temperature between this reference preform and the sample preform is not the same. So if there is any the exothermic flow, meaning that your heat is flowing from your system to the surroundings, temperature is lower here in the sample preform than the reference preform. So reference preform has a high temperature than this one, right at that point, exothermic reaction. So temperature, so you have to supply your heat to the sample preform, okay, to balance between these two temperatures, or vice versa. So we have two different types of the heat flows. The y-axis is the heat flow, and this is the temperature. This is the case. The top case is the endothermic flow cases, where the heat is flowing into the sample because of the endothermic behaviors. So the heat flow is coming right in here, okay, in this behavior. So this is the endothermic, and this is exothermic. If there is any behavior exothermic, then heat flow is right, the changes between these two baselines. Okay? So these two behavior can be due to glass transition, melting, or evaporation. So if you think about the melting, melting means that you absorb the heat from surrounding to your system, okay? Whereas the crystallization means that your larger or the unoriented or the random will become ordered structure, so your heat from your system will be going out. And that's what they call the exothermic reactions. So the curing, cooling, or the crystallization, all of them are behaving like exothermic reaction behaviors. So this is the principle of the differential scanning calorimetry. In polymeric system, we use this DSC very often. So we have here in this floor we have a DSC, and it costs and you will be able to detect the heat flow or exothermic and endothermic reactions of the polymeric systems. Now with this instrument, you can detect many of the other the parameters of your thermodynamic factors, such as specific heat capacity, crystallization, or phase changes, oxidation, stability, stuff like that. Okay? And typical curve looks something like this. Okay? As you increase the temperature of your polymeric system in the sample pan, it behaves like this. And I think this is the first, at first, if you increase the temperature, it looks something like this. And after some temperature, if you cool down, and this picture is a composite picture of this heating and cooling cycles. Okay? So anyway, this is the endothermic, exothermic, and endothermic, exothermic, and endothermic reactions. And at high temperature, okay, we can detect this is due to the melting, and this is due to the crystallization, and this is due to the glass transition behaviors. So by knowing the DSC thermogram of the polymeric system, you can detect both glass transition temperature, melting temperature, and crystallization temperature. Okay? So at one shot, you can detect the thermal behavior of the polymers. If you flip over endothermic and exothermic, it looks like something like this. And this is the typical This is the typical composite graph. Okay, if you flip over, okay? So glass transition temperature is in the endothermic, so it looks something like this. And if you increase the temperature further, then you know, it look like this. And at high temperature, of course, the polymer decomposes. Okay? Polymer will break into the small fractions, so that it decomposes. Okay. So between this initial point and final point, okay, between this initial and final point, we have two different temperature profile. Okay, initial point and the final point, and midpoint between these two is generally called the glass transition temperatures. Okay, and the midpoint here, or minimum point, whatever, maximum or minimum point here is called melting temperature. These are the general understanding of how we can measure the glass transition temperature and the melting temperatures. Now, again, I think I have still have some question left. Right? How can you measure the crystallinity by using this curve? I know that I showed you we can detect the glass transition temperature and melting temperature. But can we measure the crystallinity? Is there any clue from this graph measuring the crystallinity? Crystallization. This is the crystallization temperature, right? Any clue about crystallinity? If you have a large amount of crystals, or if your crystallinity is high, what do you expect from this graph? Or if you don't have any crystals, what do you expect from this graph? From this type of graph, in fact. Height, yes, height and area under the curve, okay, or height of this area under the curve or height could be related with crystallinity, right? If you don't have any crystals, do you expect the melting temperature? No, right? And I have emphasized several times that polymers may have a crystalline temperature, melting temperature, but glass transition temperature should be present in polymers. So all the polymer has this, endothermic behavior of this glass transition temperature, whereas polymers may not have this melting temperature, right? If you have crystals, yes, you have a melting temperature, but amorphous portion do not have any melting. So amorphous polymer has flat without any melting, whereas 100% crystals may have a high, melting peaks, or large melting peaks, or large area under the curve, whereas semi-crystalline polymer may have in between, right? So if you measure the area under the curve, you will be able to detect the percent crystallinity by knowing the standard calibration curve, okay? Standard calibration curve. So you need to, do you know the calibration curve? Well, for example, if you have several samples, at least 3, with a known crystallinity. Okay, if you prefer prepare the 0% crystallinity, 100% crystallinity, and maybe your polymer may have a 40% and 70% crystallinity. So you should have at least 3 or 4 samples, at least 3 samples. But the, higher, larger than 3 could be much more reliable. If you know the sample with the known crystallinity and measure the area under the curve in the DSC, okay, and perhaps this area under the curve might be 0 here because we don't have any crystallinity. And at 100% crystallinity, you may have an area under the curve. Well, I don't know, maybe it's 90. You can integrate them automatically in the machine. In between, perhaps it's a 60, just some number, 70, something like that. And if you get this table, you can draw the graph between the area and crystallinity. If it's 0 and 0, area might be about 90 here. It's about 100 here. You have 4 points. Right? And you can make the equation with some statistical reliability. So you measure the graph equation. So crystallinity C is equal to A plus BA, area. Okay? So you will be able to find A and B, then you can find the equation. So this is what we call the calibration equation. Okay? This is what we call the calibration equation. If you know and if you find this calibration equation by knowing the crystallinity of your known sample and the area under the curve of your crystalline portion, you can establish this equation. And if you measure the unknown sample, okay, if you measure the unknown sample and measure the area under the curve, your area under the curve could be, let's say here or here. Area under if you measure the area under the curve of the unknown sample, then this will become, you will be able to find the crystallinity. Or if you add this area under the curve, you can find the crystallinity of your unknown sample. So this way, you can easily find out the percent crystallinity. Okay? This is one way of measuring the percent crystallinity. If you have known crystalline portion of your samples. Okay. Now, second way of measuring the crystallinity can be done by the wide-angle scattering X-ray diffraction patterns. Okay? X-ray can be widely used in these days, and of course, the X-ray can pass through your body, so the X-ray can detect what's wrong in your body as well. Okay? That is the very good way of utilizing our X-ray in our life. And the second way of measuring, the second way of utilizing this X-ray is the crystalline structure and the crystalline portion of your polymeric systems using these X-rays. So in your the general chemistry course or physical chemistry course, you are familiar with the Bragg's law. Okay, so if you have crystals, okay, for example, your polymer has a crystalline portion. One of these could be a particle or the crystals. Now, distance between this crystalline and crystals are defined as a D. D is defined as interatomic distance or well, if your polymer, may have a distance, okay, and this D in your polymer system is interlayer distance or interchain distance. Okay? If it's a single molecule or the organic or inorganic particles, it is defined as interatomic spacings. Anyway, the D is defined as interspaces between the chains or between the atoms. So if you expose the polymeric system or the low molecular weight compounds with the X-ray, there's an instant beam of the X-rays, but X-ray can penetrate through, of course, but it diffracts, right? It diffracts, and you just like this, okay? And this is the principle of the light behavior of your systems. So there are some angles between the instant beam and the plane structure. So this is the theta, defined as theta, and theta is, can be multiplied by this 2. This is 2 theta. So Bragg's law says that interlayer distance or the interatomic distance D could be related with the theta, instant beam angle, and your wave number, it's wavelength of your X-rays. Okay, so by using this Bragg's equation, if you measure the theta, and because you know the lambda is the instant beam strength of your X-rays, so lambda is a known constant. So by measuring the theta, you will be able to calculate the distance between the chains. Okay? So this is the basic principle of the Bragg's law, and you're using the X-rays, and these are the sample the X-ray scattering patterns for metals, which is a crystalline polymer, a crystalline material, or the inorganic material or low molecular weight organic material with a crystalline portion, crystals. Then the peak looks something like this in 2 theta in terms of X-rays. Now this peak maxima is due to the crystals. If there is a diffraction patterns, okay, and you have at least 4 crystalline forms here. If you look at this one in the liquid phase, this is quite broad. Okay? There is no sharp peaks in the liquid phase, meaning that you don't have any crystals. It's amorphous. So if you have a sharper peaks, you have crystals. If you have a broad one or without any peaks, then means that you have amorphous. So if you look at the third one here, it's a semi-crystalline polymer below the melting temperature. And below the melting temperature, you have a rubbery portion and the crystalline portions, right? And you have a sharper peaks in the presence of amorphous, broad, the peaks. Okay, so this is the basic shape of the crystalline and amorphous polymers or the materials. How we can detect the D? Well, if you measure the theta one here, and at maximum intensity, you measure the 2 theta here. 2 theta might be 18 degree or 10 degree or whatever. Okay, if you measure the theta here, 2 theta, then you add here, and you can detect the D. So at peak maxima, you will be able to detect the distance between the 2 layers, or the interatomic distance can be such as like a 5 Armstrong, 6 Armstrong, 10 nanometer, whatever. Okay, so you can detect the distance between these two as well. So this way you can detect what kind of crystals that you have, and what is the distance between the interchain layers. If you just like what we can do in the DSC, if you integrate those area under the curve, right? you will be able to calculate, of course, the crystallinity as well. Okay, because the crystalline intensity could be linearly, almost linearly related with the percent crystallinity, right? If you have an amorphous polymer, you don't have any peak maxima, right? If you have 100% one, you have a peak maxima, which is large in area. If you have a semi-crystalline one, your area under the curve is smaller than the 100% crystalline portions. So area under this crystalline portion is quite related with your percent crystallinity. So by measuring the area under the curve of your crystalline portion, you can also detect the percent crystallinity. Now the second one, you can quantify those percent crystallinity by measuring this wide angle X-rays, and the other qualitative way of measuring the crystallinity is represented here in the bottom. You can detect you can detect the crystalline form of your polymer and take a picture through the long exposure times. You have an X-ray source, you have a colorimeter, and the screen. And if you put the pictures, I mean screens or whatever, then you can detect some type of these pictures rather than these peaks. Okay? Now this is the case of amorphous polymer. This is the case for the X-ray diffraction patterns of similar polymer. And this is the semi-crystalline polymers. Now, if you look at the next slide, I think we can see some other ones. This is the amorphous polymeric structure, whereas this is oriented the crystalline portion. This is oriented crystalline portion and the amorphous portions. Now, crystalline portion have a ring here, very distinct, rings, but amorphous polymer doesn't have the very specific rings. Okay? In this case, the third one, the C, you have rings, very dark rings, but there are some spots. These crystalline portion spots are embedded in the randomly dispersed amorphous portions. This is the typical curve for the semi-crystalline or the polymers. And the second one is the crystalline polymers. So if you look at this, you can say that this is the semi-crystalline one. Okay, the last one is perhaps amorphous polymer case, because you cannot see, large the specific hollows. The second one and the third one might be crystalline polymers, right? Because of the very specific hollows, specific lines. Okay? So this way you will be able to measure or catch the pictures, okay, of your crystalline and amorphous polymers. The last slide that I can present in this crystallinity is that if you look at this, 3 peaks. This is the case where you have biodegradable hydroxybutylate. Hydroxybutylate is a biodegradable polymer, so you can use this polymer as a suture or some sort of organic, the artificial organs, 인공장기, artificial organs. But this is it says that it has about 61% of crystallinity. This is the 46% crystallinity. It's mixed with the silk. Silk is also the polyamide, is polypeptide, and has crystalline portions. This is the silk, and it has a crystallinity of about 10%. And middle one is a mixture of PHB and the silk, so that it has about 46%. If you look at these peaks of the 3 samples, less crystalline silk polymer has a quite broad structure, looks like a quite amorphous polymer, whereas a crystalline one has a very specific sharper peaks mixed with the amorphous one. So we can detect this peak might be due to what kind of distance between the chains, right? Because you can detect the D. You can detect the D distance by measuring the 2 theta here. If you know the 2 theta, it's like a 13 degree. 2 theta is 13, so theta is about 7.5. So if you put the 7.5 in the Bragg's equation, and lambda might be 1.5 Armstrong or something, so that you can detect the, you can measure the D distance between these two layers. This one has a different D, and so on. And the peak area is pretty much larger here in this case than the second case because of the different crystallinity. So by using this, the qualitative and quantitative way of measuring the crystallinity, you can say that this is the crystalline polymer or amorphous polymer or semi-crystalline polymer, or you can quantify them, saying that this has such percent of crystallinity of your polymer systems. Okay. Okay, so this is what I can say about the percent crystallinity and crystallinity in chapter 4. Okay, for those of you who cannot speak Korean, I think I need to explain what his question was. His question was how we can detect the percent crystallinity by measuring these peaks in X-rays. Okay? Well, that's a very good question, okay, in quantification of the polymer systems. If you look at these peaks, 3 peaks, these are the same scales, right? These are the same scales. Now, if you look at this amorphous one, almost 10% one, is very, very broad, without any sharper peaks, and it appears like a 20 degree here, right? And it looks like that these above this 20 is more like the amorphous ones. Looks like amorphous ones. But anyway, if you integrate them between here and here and here and here, these are due to the crystals, very definitely. So this is the area you can detect these two. The third one and fourth one might be due to the crystals as well. If you think this is due to the crystals, then you can align here, and this machine will automatically integrate the area. So it gives you the number. So you add area under the curve here, area under the curve, area under the curve, area under the curve. So you have a 4. You have area under the curve here, here. Area under the curve is quite a little different. This is about, well, this might be due to the crystals, but area under the curve might be very small, which is undetectable, I would say. It's almost zero. I don't know how they can calculate the 61% or 46%, but this is the way of measuring their crystallinity and getting the after getting this calibration curve, let's say. Okay, pretty much similar to what we can detect in the DSC. Any other questions about the crystallinity? Okay, if you don't have any the questions, I think I can I can talk a little bit about the other aspect of the crystalline portion. Let's see this curve. Okay. Now in this curve, you can detect the glass transition temperature, right? You can detect the glass transition temperatures. Let me ask you, if your glass transition temperature is about 80 degrees C, if the material has I have two materials. One has a TG of 80 degrees C, and I have a second material where the glass transition temperature might be minus 20 degrees C. Okay? And let's imagine what kind of property of these two materials can have. What kind of property? The first material has a TG of about 80 degrees C. So TG of about 80 degrees C. So 80 degrees C is right in here. And the second one has a TG which is about minus 20 degrees C. Although the shape is the same and two material has a glass transition temperature, but glass transition temperature, two materials are different. You are living at room temperature, right? We are at room temperature. Room temperature is what? About 25 degrees or something like that, right? So think about these two materials at room temperature. At room temperature, the first material has a TG of about 80 degrees C. So room temperature is below the glass transition temperature. So it's right in the left-hand side of your TG, right? And below TG, your material is glassy, right? Glassy. Above TG, your material is rubbery, glassy and rubbery. So the first material at room temperature, TG is higher than room temperature. Whereas the second material, room temperature is above the TG, right? TG is minus 20 in the second case, whereas your room temperature is higher than TG. So your material is behaving like a rubber, right? So by knowing the TG, you will be able to find the property of your materials. The first material is a glass material. Second one is a rubbery material. Glass material has a TG above the room temperature, whereas the second material has a TG below the room temperature, right? So I'm showing you two materials. This is the safety glass. So when you go into the laboratory, you should wear the the glasses, the plastic glasses. This glass is glass because it's a glass material. Okay, this is made of polymethyl methacrylate, PMMA, and I think I showed you the structure. PMMA is a transparent material. This is the organic glass, and it's glassy. Okay, glass material is a rigid material. It's not flexible. It's easily broken if you apply the pressure, but it has a lot of good property as well. Okay? This is an example of the glassy material. So the TG is always higher than room temperature, right? Second example is rubber material. Okay, rubber material always has a TG below the room temperature. If you think about the Scotch tape, and I showed you that the Scotch tape on back side of your film it has a sticky and rubbery, flexible adhesive. Okay, all of you may have the post-it note or whatever the tape, and backside of this film you have a sticky material. This is sticky material has a rubbery flexible material, and it's composed of polymethyl acrylate or polyoxyacrylate, depending upon how strong your hydrogen bonding is. If your side chain is only methyl group, then it's less. It has a very strong sticky property. Whereas if it's a long side chain, then it has just like octyl group, it is less sticky. Okay. If you think about the two Scotch tape, first one is a lowering one, is pretty sticky, and the sticky one has a methyl group in your polyacrylate. Whereas the post-it note is less sticky, just like this one. Okay, you can release, you can press them or you can release them without any trouble. You can put it on top of your paper and detach it without any problem. It's less sticky. And less sticky one has a long side chain. Therefore, the hydrogen bonding between the carbonyl and carbon and the hydrogen is less because of the long side chains. It has an octyl group, whereas the less pretty sticky the Scotch tape has a methyl group or ethyl group. Okay, because it's a short side chain. So depending upon your the length of your alkyl group, it has a different glass transition temperature, but those glass transition temperature of this sticky material is always lower than the room temperature. I have an eraser. Okay, this is the rubber, of course. This rubber is a flexible one. So that's why we call this is a rubber. Rubbery one has this glass transition temperature below room temperature. So you can imagine you don't know what's the number of your TG, but anyway, TG is not higher than room temperature. It could be 10, it could be minus 20 or whatever, but it's not higher than room temperature. And although the shape is the same, you see where is your room temperature. If your room temperature is right here, if your room temperature is right here, depending upon where your room temperature, your material behaves differently. Okay. Third example is, think about your TG of your fibers. TG of your fibers. You are wearing the fibers, acrylic fiber, polyester fiber, silk, or wool, or whatever. All of those fibers that you're wearing has a TG. Most of them are above the room temperature, right? Above the room temperature, except the 쫄바지. Okay, the 쫄바지 has a very flexible one. So the flexible one has a lower the glass transition temperature. It's not as low as a sticky Scotch tape, but anyway, it's lower than room temperature. So magnitude of your distance between room temperature and TG, okay, will tell you how the stable of your material is and what is the state of your material is as well. Distance between the room temperature and TG will tell you the stability of your materials. Now, this material has the PMMA. PMMA has a glass transition temperature of around 80 degrees C. This is the first case. But I think I lost my, all my precious samples like a Kevlar or Nomex. Okay, the ones that I showed you in the first time, has a TG above 400 degrees C, which is very stable one. So the distance between your room temperature and the TG will tell you how stable your material is. Okay, this is the story that I can tell you about the crystallinity and the structure and properties and so on. And next time, I think I will tell you about the molecular weight. Molecular weight. In chapter 5, I will, upload this file shortly, but we can discuss about the molecular weight measurements. Okay? Because the polymer has large molecular weight or high molecular weight, and we need to know how high, okay, how high the molecular weight is, and the measurement of molecular weight is very important. Okay? If you synthesize your polymer and molecular weight is lower, your property is not the same as the material with high molecular weights. So you have to know about what is your critical molecular weight is and how you can detect your molecular weight. And there are 4 ways of measuring the molecular weights. So please read this chapter in the textbook and the material that I will give you. So how we can measure the molecular weight of your polymer, and there are 2 ways of measuring the molecular weights: absolute weight, absolute molecular weight, and the relative molecular weights. And these molecular weight will affect your polymer properties. Okay, and there are several sites that I have downloaded. So if you click them, you can even make the virtual experiments of measuring the viscosity and the molecular weights. Okay? So if you click those sites, please do so. But before coming to the class, please read these materials and ask me the questions if you might have. So we can talk about the molecular weight in chapter 5 next week. And finally, I think I would like to take the quiz on about the structure and names on next Saturday. Next Saturday, which is 30, which is about 29.
Yeah.
29, right? 29 at 7 a.m. No, it's at around I think I would say 9:30 a.m. Okay. 9:30. 9 a.m. 9:30, right? 9:30 here, right? Because they are taking the tapes, I think it's not appropriate to take a quiz with the taping schedule. Okay, so I would like to pick up the Saturday because I have 1 hour missing 2 weeks ago. Okay, with that, I'll see you on next Wednesday. Thank you.